We're going to begin with a review of rotating complex numbers. Suppose we have these three complex numbers, P, Q, and W, and we want to find this angle between P and Q. We'll note that translating these 3 points will not affect the angle, so let's move omega down here to the origin, and we'll call this omega prime. And we'll make the same translation that we did to omega to P and Q. We'll call this P prime and Q prime, and this is also theta. So the translation of omega to omega prime, that gets us to 0, just amounts to subtracting omega. So we'll do the same thing to P and Q to get P prime and Q prime. And recall that rotating is basically the same as multiplying by an exponential. So if we want to rotate some complex number written in exponential form, se to the I phi, by some angle theta, we can accomplish that by multiplying by e to the I theta. Because of our property of exponents, we add the exponents, which has the effect of adding theta to our starting angle. So if the distance from P to omega is the same as the distance from Q to omega, this goes the same for P prime omega prime being the same as Q prime omega prime. We can then get to Q prime by rotating P prime. We'll make our substitutions here for P prime and Q prime in terms of P and Q. And if we want to figure out what theta is, then we can divide by this coefficient. So the argument of this quotient is the same as the angle between P and Q around omega. Let's return to the problem statement. We need this product to be a real number. So first, let's figure out what it means for the product of two complex numbers to be real. We'll multiply this out and collect the real and imaginary terms. So in order for this to be real, we need to get rid of this imaginary part. This means this coefficient of I is 0. Let's divide this by A and B. We'll make these ratios equal to a constant K. So C is K times A and D is minus K times B. We'll substitute in for this product and factor out the K. So if we take any complex number and multiply it by a scalar multiple of its conjugate, we'll get a real number. So if this is our original complex number with an angle theta, then some multiple of its conjugate with an angle of negative theta, the product of these two complex numbers will be real, which means their angles will be opposites. It might be easier, though, if we can think about them having the same argument. So, for example, if we have one complex number written this way in exponential form, and then a second complex number, if we find the quotient, we get this expression over here. If we want this to, again, be a real number, then we need this angle above the real axis to be 0. That means theta and phi are the same argument for our original two complex numbers. So we know that if we multiply a number and the reciprocal of another number, we'll get a real number as the product if the angles are the same. So let's take a look at this expression. Here's our first complex number, and I'm going to take the reciprocal of the second complex number. So that's going to be z minus z3 over z minus z2. If the product of these two numbers is real, then they both have the same argument. Let's graph z1, z2, and z3. z1 is over here. z2 has the same real part, and this is z3. And again, we want the arguments of these two complex numbers to be the same. I'll connect these points. This is z3 minus z1, and this is z2 minus z1. And here is our angle theta. Recall that we can use the quotient of a difference that looks like this, find the argument of it, and we'll have the angle between these complex numbers. This means that there is some other complex number z that forms the same angle theta between z3 and z2. Maybe it's over here, where this angle is also theta. These two congruent angles that share these two common points, z2 and z3, but have different vertices, might remind you of inscribed angles in a circle. Let's redraw this in a circle. We'll draw z1 and z2 so that they share the same x-coordinate, and we'll put z3 over here, and we'll draw this angle. And then we have some other point z. This will also have the same angle. The problem statement asks us to maximize the imaginary part of this number z. That's going to be at the top of the circle, directly above the center, which I'll call O. If we can figure out the y-coordinate of O, then we should be able to find the real part of z. We can use our property of circles by drawing a segment from the center of the circle to the midpoint of z1 and Z2. I'll just write these coordinates now as if they were in the Cartesian plane because the calculations are the same. This midpoint is easy to find because it's just the average of the y-coordinates of Z1 and Z2. To find its x-coordinate, we'll just note that this perpendicular segment from O to the line connecting Z2 and Z3, this line OP will be perpendicular to Z2, Z3. So let's find the slope between Z2 and Z3 as if they were in the real plane. This ends up being 1, so the slope from O to P is -1. So the line that passes through OP, if it were in the real plane, would look something like this. To figure out K, we'll find P, which is also the midpoint of Z2 and Z3. So we'll take the average of the x-coordinates and y-coordinates. That means P is at 48,69. Since P is on this line, we can plug in for x and y to get K. And we have the y-coordinate of O, and since O is on this line, we'll figure out its x-coordinate. Its x-coordinate then is 56. Since we're maximizing the imaginary part of Z, and Z can be anywhere on this brown circle, then we'll place it directly above O with the same x-coordinate. So the real part of Z is also 56, and that's our answer. If you'd like me to solve any other math contest problems, please leave them in the comments.